So in our last class, we started discussing about digital image processing. And we said in our last class, there are three major steps in digital image processing: image pre-processing, image analysis, and the image understanding. So the first step is image pre-processing, which is critical for designing effective and efficient image processing based systems. Because the first step is we have to make sure that the image has good quality naturalness for recognition, for identification, for verification, for detection, for the systems that we want to design. So when we are trying to make sure that the image is with good quality and naturalness, there are different tasks that we have to perform, like skew detection and the correction, like normalization of the size of the image, like image enhancement and image restoration. Especially image enhancement and image restorations are critical in most of image processing tasks, because whatever image you are getting, that image at some point may lost its quality and naturalness. When we are digitizing, since there is an approximation, we are losing some quality. When we are compressing again, either using lossless or lossy, there is an image degradation. When we are sharing the image, again, because of devices malfunction, maybe there is a degradation of image. So we need to filter the image before using it for any application. So the filtering will make sure that the image is with a better quality or naturalness. So we can do filtering in a spatial domain or frequency domain. Most frequently, we are using spatial domain because spatially noises can easily be predicted using different techniques. But if it is image enhancement, and if the image has a periodic noise, we have to go from spatial domain to frequency domain, rather than just dealing with frequency of occurrence of pixels in a given image and compare them with the crater window. We have to transform the image itself into frequency domain and try to understand how pixels are transiting from one intensity to another intensity. So the major step we have is filtering, image filtering to reduce noise in a spatial domain. And there are many techniques available. Mostly we are using mean filtering, median filtering, Gaussian filtering. We know mean filtering, a filtering technique designed based on the principle of mean. The same thing in the case of median filtering also, a filtering technique designed based on the principle of median. And even nowadays also, there is a new generated filtering. Rather than just using the max and the mean, we can combine the two, divide by two, then take the average of maximum and the minimum. But still, the usual way of checking is first median, then mean. Again, filtering can be divided into linear filtering and non-linear filtering. Filtering using non-linear as compared to linear, it's not summing over the pixels that we are considering against the windows that we created. Like median filtering, they are just trying to see only within the window which part of the pixels are dominating in that given window. The same thing for mean filtering also. So how can we calculate mean filtering? And how can we make an adjustment in our image using median filtering. We know that the mean is calculated by summing over all frequencies over the number of frequencies we consider. For us, we are trying to check the given window, and within that window, the pixels values. So we are summing over the pixel values that are lying within the window, divided by the number of pixels that we consider. Consider the example, which is a grayscale image, and we are using a window of 3 by 3. So we are considering 3 by 3 windows, 3 row wise and 3 column wise. Then we are trying to make sure that the middle, the central pixel is the value that is expected to have. But that one is checked against the surrounding pixels using mean filtering. So mean filtering is taking all the pixels that are lying within the 3 by 3 window, sum over all the pixel values, and divide by the number of pixels. If you consider the one in a red box, if you add over all the pixel values, there are 9 pixels because 3 by 3, and the sum is 19, and then the number of pixels considered is 9. 19 over 9 is 10. So the value of the central pixel is not 19. Rather, the exact value determined based on the neighboring pixels is 10. So we have to adjust the value at that point to 10. Take also another one. For instance, at this point also we have 0. But if you calculate by taking a 3 by 3 window, around that 0 are all with 19 values. So 8 times 19 is 720. 720 divided by 9 is 80. So the value of this pixel is not 0. Rather, it is 80. So in such a way, all the adjustments are made based on by creating a 3 by 3 window or a 5 by 5 window. Which window is optimal? It will be decided based on experimentation. Which one is giving us a better quality image? That one should be decided based on experimentation. So for the time being, using a 3 by 3 window, still we can calculate using 5 by 5 also. The number of pixels are increasing from 9 to 25, but still by looking around a given pixel, those 25 pixels, we can decide the value of the central pixel using mean filtering. In the case of median filtering also, we follow the principle of median. Median is calculated by identifying the value that lies at the middle of those considered number of pixel values. First of all, we have to sort them in ascending and descending order. Then take the middle value. Mostly for median filtering, it's better to take an odd window. That means a 3 by 3 window or a 5 by 5 window, rather than a 4 by 4 or 2 by 2. Because if you are taking even valued window as the center of any even valued windows, there are 2 numbers. So we have to again find mean of those 2 values. That one may be not efficient, and even creating some noises at the end points of edge of the image. So it's better to go for taking a 3 by 3, 5 by 5, or 7 by 7, which gives us an odd number of pixels, out of which one of them is only lying in between. Nowadays, median filtering is effective, especially for salt and pepper noises. which is distributed all over the image. How can we do that? For instance, in this example, there is an image which is corrupted by a salt and a pepper noise. Take this image and use median filtering, you'll get a better clean image by removing those distributed noises over all the image. How can we calculate the median filtering? Just follow the principle of the median. Identify the values that we are considering in a 3x3 window. In a 3x3 window, there are 9 pixels. Take those 9 pixels and then sort them in ascending or descending order. Pick the middle pixel and compare that middle pixel with the pixel at the center of the 3x3 window. Then replace that 3x3, the central pixels, with the median filtering identified using the 3x3 or 5x5 window. So in all the cases, window is critical. So we are using that window for calculating the pixel value and then compare it with the existing pixel value. If it's different, we have to replace it with the new pixel value calculated using median filtering or mean filtering. So given just we take only the 3x3 image and assume that we are also using a 3x3 window and we want to calculate the value of the pixel as the center of the image. That is with the value 8. If we use median filtering, since we are considering a 3x3 window, so there are 9 pixels and sort them in ascending order. And as the center of 9 pixel values appears at the fifth, and that fifth value is 111333789. The fifth value is 3. So according to median filtering, the value of this image is not 8 as per evaluation of based on the nearby pixels in a 3x3 window. It should be replaced by 3 according to median filtering. But if you are using mean filtering, it may give us a different number, because according to mean filtering, given the 3x3 window, we have to sum over all the 9 pixel values. That means we have here 10, 27, 30, 33, 33 over 9 will give us some values between 3 and 4. So in this case, it's more of approximated to 3. So since we know from our statistical knowledge how to calculate mean and the median, we can easily determine the correct values of a given pixel based on the windows that we are considering for evaluating the correctness of that given central pixel. Here it asks about given the original image, we are expected to check whether those in a yellow colors are the correct values or not. Towards checking them, if you use the median filtering, either A or B or C is correct. A is not correct even from the beginning. If you evaluate the pixel value of 5 based on a 3x3 window, the value that should be given for the pixel value of 5 is 2 rather than 5, because most of the pixels around the pixel value 5s are 2. So it has to be replaced by 2. But the next pixel is with 2. And if you see around that pixel, most of the values are 2. So there is no need of touching it. But in the case of A, it's replaced by 5. This is wrong. But if you take B and the C, they are giving us the right values. But if you go down to the 4th row, B is taking 333, but C is suggesting 377. For the pixel value 3, if you evaluate around that in a 3 by 3 window, yes, the right value is 3, because at the 5th position, we'll get 3 if you sort 2, 2, 2, 3, 3, 3, 3, 4, 7. But what about for this 7 value pixel? If you see around that 7, 1, 2, 2, it should be 3, no 7. So rather than C, it's better to go for B. So B is the correct answer out of ABC for the given image. When you are applying a 3 by 3 windows by applying median filtering. So you can exercise on this picture. The other filtering techniques are linear spatial filtering, like correlation and convolution. Again, they need window for evaluating a given pixel, but they are a linear spatial filtering techniques. In a linear spatial filtering techniques, as compared to the median and the mean, here we are finding the weighted sum of the given window times the given image. So we are multiplying the 3 by 3 original image by the 3 by 3 given window or kernel. So another name for window is kernel or mask, because it's used for evaluating every pixel points. So we are trying to find in correlation and the convolution the weighted sum of the nearby pixels to the given central pixel. So given this image with 10, 5, 3, 4, 6, 1, 118 pixel values, if you use a kernel or a window with 3 by 3 and given the values of the 3 by 3, we are trying to find, in the case of correlation, the weighted sum of the 3 by 3 window against the 3 by 3 original image. So we are summing over the kernel values multiplied by the original image pixel values. So if you evaluate the correctness of the central pixel value 6 by weighting over all the image values by the kernel values, that means 0 times 10 plus 0 times 5 plus 0 times 3 plus 0 times 4 plus 0.5 plus times 6 plus 1 times 0 plus 0 times 1, 1 times 1 plus 8 times 0.5. Only we have values at 3 point. That means 0.5 times 6, 3, plus 1 times 1 is 1, 4, plus 8 times 0.5 is 4, 4 plus 4 is 8. So according to correlation linear spatial filtering, the value at this point is not 6. Rather, as per our evaluation using the given kernel, it should be 8. The same thing you can do also. Given this image, if you apply the window or kernel or mask with this 3 by 3 window, we are trying to find, for instance, the pixel value at 14. We are trying to bring the window to fit to this point, the 3 by 3 window. Then we are trying to find the weighted sum over all image pixel values multiplied by the window values. That means when you are bringing this window over the given 3 by 3 image pixels, considering the central pixel 14, so we are multiplying 8 by 1 plus 1 times 8 plus 6 times 15. So in such a way, we are finding by laying the given window over the given space, considering the central pixel, then finally we'll get a correlation value for this point with a pixel value 14 is 585. So it means the image is a color image rather than a grayscale image or a binary image. To make it a grayscale image or binary image, we have to reduce the pixel values of the windows that we are taking. You may use 1 or 0 or some numbers in between 0 and 1. So based on the given correlation, cross correlation is also designed. If you compare correlation with convolution, correlation is taking the given window as it is, just by fitting that 3 by 3 window on that given image by considering the central pixel. But in the case of correlation, we are not taking the window as it is. The window should be rotated 180 degree. Rotating 180 degree means bringing the third row to the first row, such that when we are rotating 816, 357, 492, 180 degree, 294 becomes in the first row, 753 in the second row, 618 in the third row. Rotating 180 degree means first rotate the window 19 degree, then again rotate the same window 19 degree. When we are rotating this window 816 19 degree, 438 becomes at the top, followed by 951, then 276. If you again rotate it, so you will get 294, 753, 618. So that 118 degree rotated window is used in the case of convolution for finding the most probable pixel value at every pixels within the image. The only thing is, like we do for correlation, we have to also fit the given 180 degree rotated kernel or window to every pixels within the image by taking into account the central pixel within that lies within the given kernel or window. So if you calculate for the same windows that we calculated in the case of correlation, given given window 816, 357492. When we are rotating it 180 degree, we will get 294,753,618. So we are using 294,753,618 in the case of convolution. So that window is fitted to every pixels by considering the central pixel that we are evaluating to know whether the values of that central pixel is the correct value or not. So in this case also, once the kernel or the window is rotated 180 degree, then we have to find the weighted sum of the 9 pixels that we are considering to evaluate the correctness of the central pixel value. So in such a case, we are doing the same thing, except the same thing like correlation, except the need for rotating the window 180 degree. So in this case, we are getting 575. The use of convolution is good, especially to correct any added noises by median filtering or mean filtering. So it will help us to smooth the image. The other one is Gaussian filtering. Gaussian filtering is basically designed for Gaussian noise. So in Gaussian filtering, we are using this formula. Using this formula, we are running it over the given image. Then, as per the formula, it will try to evaluate every central pixels and then switch to whatever calculated values that central pixel. The other one is the morphological processing. As we said last time, image enhancement, image restoration, and the morphological analysis are the 3 major techniques we use during image pre-processing to make sure that the image has with good quality and the naturalness. Those filtering techniques we discussed in a spatial domain, and also there are transformations that are working within the frequency domain, like Fourier transform, cosine transform, Laplacian transform. But all those different filtering techniques, whether in spatial domain or frequency domain, while they are trying to approximate the correct pixel value, they are also adding something wrong within that pixel value, especially at the edge of the image. So to correct the shape of the image, to correct the structure of the image, we need morphological analysis, which are trying to check for us to what extent the shape is correct. Maybe since the image has foreground and background, maybe the foreground is affected or the background is affected, while we are expecting at a given point white pixel, maybe it is switched to black pixel. While we are expecting black pixel, maybe it is switched to white pixels. That means while we are expecting a pixel representing a picture, maybe that pixel is switched to background, to the non-picture space. So to correct these things, we need the morphological processing. Morphological processing has 2 major operations: dilution and erosion. Dilution and erosion, the name itself is, when you are diluting, you are trying to recover the foreground pixels. But when you are eroding, you are trying to recover the background. So dilution is trying to add pixels or picture elements. So it is trying to switch zeros into ones. That means the background is switched to the foreground. But when we are talking about erosion, it's trying to erode the foreground pixels. That means the picture elements are converted into the background pixel element. So ones are converted into zeros in binary image. Mostly morphological operations are applied after binarizing the image to get a better result. That doesn't mean it's not possible to apply it in a grayscale image. Possible, but it's good to go for binary image, especially when we are applying morphological operations. But anyway, through experimentation, we have to see which one is working better. Whether by applying morphological analysis on binary image or grayscale image. Because to what extent noises are available in the image matters a lot. Whether image filtering techniques or morphological processings are working better or not. So how can we make sure that through morphological processing recovering the structure of a given image, again like we do for filtering techniques, here also we need window, which is also called structural element. Why? Because mostly it's taking the structure of the image. So we have to create a structural element, that means window of 3 by 3, 5 by 5. Then make sure that whether the central pixel is switched from 0 to 1 or from 1 to 0. So the structural element or the window that we are creating matters a lot. For binary image, we have to create either zeros or ones or a combination of them. Then after creating the structural element, we are running that structural element or window over the whole image to make sure that the image is containing the right pixels combinations. Background as a background, foreground or picture element as picture element. Basically, we are running either dilution or erosion or one after the other.